I guess not. Let me also share this on the Discord. How do we invite folks?
There's a lot of people registered for this one, but I can share the Luma link.
Let me do it.
Got it? Okay.
Yeah.
Eugene, I have a question. You mentioned in the description of the Luma, please
Yeah.
read the paper. If you have time, try the grok section 3.1 with your favorite AI teacher. Who's
Yep.
your favorite AI teacher?
Oh, Claude Opus.
Claude Opus.
Yeah.
Oh, interesting. I never used Claude for papers.
Oh, really? I have it because I
Yeah.
just have a Mac subscription. That's why.
I hate it. I don't know. I think I should try GPT-5 as well, but I just use GPT-5 now.
Okay, I think we will just wait one more minute. And
Give it a
then
few minutes. I feel like we have a lot of people registered.
yeah.
Unless you have long session, then just kick off.
I do have a lot
Okay, kick
I
off.
want to share. But we can wait one more minute, 1 or 2 more minutes. I'm gonna start with the demo, and we go into the paper, and we go in code, and then at the end we have live demo, where I'll take in requests from folks to just just provide the input prompt, and we'll see what happens. This model is currently only trained on 1 epoch, so we'll see.
Wow. Michael is new to Paper Club. So basically every Wednesday we do a different paper. We love volunteers if you want to volunteer to share something. Otherwise, it's mostly me or Eugene or someone. This paper club is kind of whatever's latest or new, whatever gets shared, someone will cover it. And then some people are experts in domains, like Eugene is the god of RecSys, so he's sharing latest state of the art of RecSys stuff. This week, yeah, that's what he's going to talk about. Next week, we have the paper, How Much Do Language Models Memorize? The week after, someone has added vision towards GPT OSS. So I think we do that one. It's like a RLVR. There's also a news research technical report. We can get one of them to present, but honestly, it wasn't great. So I think we skip it. But yeah, if anyone also wants to volunteer papers or, if you want someone else to share them, we have active Discord, just share and then someone will do. RJ presents a lot too.
Yep. Okay, so I'm gonna just get started. I won't be able to look at the chat. Also, let me know if the font is too small. And because I'm just doing this on my own laptop. So let me know if the font is too small. Okay, cool. So what do I want to talk about today? Wait, am I sharing the wrong screen? Wrong
You're
screen.
sharing your whole thing. Okay.
I need to move Zoom to this desktop pane. Perfect. And now I want to share this desktop. Can you see this?
Yes.
Perfect. Okay, so what is this? Recommended systems with generative retrieval. Let's start from the back. What is it that we want to achieve? Here's an example of what we want to achieve, whereby given this is literally the input string. Recommend PlayStation products similar to this thing. So what is this thing? This is the semantic ID. You see that it's in harmony format. We have a semantic ID start. We have a semantic ID end. And then we have 4 levels of semantic IDs. 1, 2, 3, 4. How to read this? It's hard, but we have a mapping table. So over here, recommend PlayStation products similar to this semantic ID. I have no idea what this semantic ID is, but I have a mapping table. So you can see this semantic ID is actually Logitech gaming keyboard. So when I ask for PlayStation products, it's able to say PlayStation, gaming headset for PlayStation. This is I don't think this is this is for PC, so that's a little bit off there. And this is for PC, PS5, PS4. So that's not too bad. Now let's try something else a little bit different. Recommend Zelda products similar to this thing, which is New Super Mario Bros. Is able to respond Zelda. Okay, this is off Teenage Mutant Ninja Turtles and Nintendo Wii. So I guess maybe we don't have a lot of Zelda products in the catalog. Well, let's try something a little bit different. Super Mario Bros. Meets Assassin's Creed. What happens? We
Eugene,
get Batman. Oh, go ahead.
quick question. What is this SID tool? What does semantic ID mean? What are these tokens?
That's
Like
a
at a
great
high
question.
level.
So semantic IDs are a representation of the item. So here's how we try to represent the item instead of a random hash, which is what the paper says. We will just represent an item. So imagine we try to merge something cute, Super Mario Bros, with something about assassination. Well, we get Batman. So this is an early example.
Oh,
Maybe let's just
no.
try.
You get Lego Batman. The Lego part makes it cute.
Yeah, the
Batman makes
Lego.
it. It makes
Yeah,
sense, right? Cute
let's try
Lego.
Resident Evil with Donkey Kong. Okay, maybe this is a little bit off. But I don't know, dog. Let's just say dog. I have no idea whether this is in the training data, how this would look. Dog and Super Mario, well, it's not. So you can see it defaults to Zelda because there's a very strong relationship between Nintendo, Super Mario, and Zelda. Actually, Sega. I actually wonder if this is in the data set. Luigi, Dragon Ball, Brutal Legend. So essentially, we have recommendations. We can learn the recommendations, but now that we can use natural language to shape the recommendations by cross-learning recommendation data with the natural language data. So now that is the quick demo. Hopefully you are interested enough to pay attention to this. This is, I'm going to go fairly fast and I'm going to go through a lot. We're going to go through paper. We're going to go through my notes and we are going to go through code. So I hope you give me your attention. Oh, Vibu has a hand raised.
And then a quick question on that example. So right now you're crossing stuff that should be in training data, right? So stuff like Zelda, Batman, Assassin's Creed, Resident Evil. This should
Yes.
also theoretically just work with natural language, right? So if I was to ask something like single player and something
Ooh.
like a single player game or like a multiplayer game like Zelda, right? Because Zelda is multiplayer or, multiplayer game like Zelda. And I would hope I get something
On
that's like a
country.
Nintendo game. So like maybe like Mario Kart is similar to Zelda but multiplayer, right?
Let's try this. This is the amazing Spider-Man. We know this because there's the output is the past of the this is the actual output, which is in SID. This log over here is the past. So this is recommend single player game similar to Spider-Man. Okay, Batman, multiplayer. I don't know how this will work. And this is a very janky young model. Well, it's still Batman. Well, maybe doesn't work very well.
Some Batman games are multiplayer, but I mean I think the point is yours is like a toy example, but
Yeah.
I just wanted to clarify theoretically that should work, right?
Yep, theoretically it should work if we have enough training data that we augment well enough. I haven't done a lot of data augmentation here, but now let's jump into the paper. So this is the paper. The blue highlights essentially mean implementation details. The yellow highlights are interesting things. Green is good, red is bad. So most recommender systems, they do retrieval by doing this thing, which is we embed queries and items in the same vector space, and then we do approximate nearest neighbors. So essentially all of this is always standard, embed everything and do approximate nearest neighbors. But what this paper is suggesting is that now we can actually just decode, we can get a model to return the most similar products. So now this is of course very expensive compared to just approximate nearest neighbors, which is extremely cheap. But this gives us a few special properties whereby now we can tweak how we want the output to look like, as you can see with just natural text. And we essentially, it allows us to kind of filter our recommendations and shape our recommendations. So now imagine that if I were to imagine a chatbot capability, right? Like this. Okay, let's say we have Zelda, and assuming it's better trained, Super Mario Bros. And I want more Zelda products similar to Super Mario Bros. We get one of these. Well, only one, but we'll see essentially just more training data needs more training data and augmentation. So over here now we get 3 Zelda products. Of course, the temperature here is fairly high. Essentially, I'm just trying to test how this looks like. And you can see by suggesting the model understands the word Zelda, the model understands this product, and the model understands products similar to this product, but in the form of Zelda. So that's what this paper is proposing. Again, Vibu.
Yeah, is this meant to be like used in real time, low latency, small model situation? Or like, honestly, from an external perspective, it just doesn't seem that like it doesn't seem super clear what's special about this, right? Because if you just ask any model, like you ask Gemini or ChatGPT or anything, recommend me multiplayer games similar to Zelda, you should know
Yep.
this, right?
Yeah, what I think is unique about this model. So imagine if you just ask a regular LLM, recommend me all multiplayer games unique to Zelda, it will recommend you games based on its memory and based on what it's learned on the internet. So what is unique here is I'm trying to join world knowledge learned on the internet and customer behavioral knowledge, which is proprietary and seldom available on the internet. So I'm trying to merge those together. So usually when you use world knowledge, there's a very strong popularity bias, right? But when you try to merge it with actual behavioral knowledge that's progressing in real time, and you can imagine mapping it to things like this, you can get that kind of data. So that's what I mean by this is a bilingual model that speaks English and customer behavior in terms of semantic IDs.
I see. Very interesting. And the like more clear-cut example would be like LLM would be out of date because there's knowledge cut off. But if you have like a new song or something, it can
Exactly.
okay.
Yeah,
Someone
like
else
this would
has
solve.
hand raised.
Oh, another hand raise.
Yeah.
Yeah, so what if the world knowledge and the local knowledge conflict? So what will happen then?
I don't know. Yeah, I don't know. I guess it really depends on. So there's world knowledge, right? And then when you maybe fine tune this on local knowledge, it depends on how much strength you want to know local knowledge to update the weights.
Okay.
Yeah.
Okay. Yeah.
So
Like
while it's go ahead.
from basic training principles, the local knowledge should always come first, right? Because let's say like you have a base model that thinks, if someone likes Zelda, they like Mario Kart. But if you've trained it such that people that like Zelda prefer some other category of game, your model is trained to, predict one after the other. So the later training often has more impact.
Yeah, I mean, so the reason why I asked is because there's a lot of abundance of evidence in the like base model. So by just having one example, does that completely override the information it has learned with so much evidence? I don't know. It's a good test, I guess.
Yeah, honestly, I don't know. So that's where this is what I'm trying to explore. Well, we're already 15 minutes in. Barely touched anything I want to cover, but I'm going to try to speed through this a little bit faster, and I'll stop for questions maybe at the 45-minute mark. So now most systems nowadays use this retrieve and rank strategy. Essentially, here's the approximate nearest index I was talking about over here. Given a request, you embed it, you get approximate nearest neighbors index. And as you add features, and then you try to do some ranking on top of it. This could be as simple as a logistic regression or a decision tree or two-tower network or whatever, a SASRec. We actually look at a SASRec, which is essentially a 1 or 2 layer auto decoder model that is trained on user sequences. We'll look at that later. So how they are trying to do this is they have a semantic representation of items called a semantic ID. So semantic ID, so usually product items or any item you represent is usually a random hash, like some random hash of numbers. This semantic ID, and we have seen, is a sequence of 4 levels of tokens. So now these 4 levels of tokens, they actually encode each item's content information. And we'll see how we do that. So what they do is they use a pre-trained text encoder to generate content embeddings, and this is to encode text. You can imagine using a clip to encode images, using other encoders to encode audio, etc. Then they do a quantization scheme. So what is this quantization scheme? I think this is very important, and that's why I wanted to take extra time to go through section 3.1 of this. So here are the benefits that they expound, right? Like training and transformer on semantically meaningful data allows knowledge sharing across items. So essentially now we don't need random IDs. Now, when we understand one item in one format, we can now understand it a new item. So now for a new item, if we have no customer behavioral data, so long as we have a way to get the semantic ID for it, and because the semantic ID for it, the assumption is that the levels of the semantic ID, the first level, the second level, the third level, we'll find a similar item, we can start to recommend that item as well. All right, so essentially generalized to newly added items in a corpus. And the other thing is the scale of the item corpus. Usually, on e-commerce or whatever, the scale of the items is like millions and maybe even billions. So when you train such a model, your embedding table becomes very big, right? In the order of millions or billions. But if you use semantic IDs, and if a semantic ID is just represented by a combination of tokens, we can now use very few embeddings to represent a lot of tables. And I'll show you what I mean by this. The first thing I want to talk about is how we generate semantic IDs. So one of the previous ideas was using a vector quantization recommender. So it generates codes that are like semantic IDs. What they use is an RQ-VAE, Residual Quantization Variational and autoencoder. I think this is quite important, like how to train a good RQ-VAE that leads to semantically meaningful semantic IDs that your downstream model can then learn from. I think it's quite challenging, and I haven't found very good literature or understanding of how to do this well. So this is their proposed framework. First, given an item's content, be it text, audio, image, or video, we encode it to, first we get the vectors, then we quantize it to semantic code words. That's step number one. Second, now once we have these tokens, these semantic tokens for an item, we can now use it to train a transformer model or language model, which is the demo I just showed you. So I'm going to take a little bit of time to try to help us all understand what residual quantization means. So essentially, given an embedding, okay, given an embedding that comes in, we consider this the residue. We think of everything here within this gray box as residuals. An embedding comes in, we consider it the first residue. We try to find which codebook token it is most similar to, and we assign it to it. Right. So now we've assigned it to codebook token number 7, and it's the most similar. So then what we take is we take the initial residue that comes in, the initial embedding that comes in, this blue box, we subtract away the embedding of the codebook token 7, and now we get 1. Right. This remaining thing here, this is the remaining residue. Then we repeat it at codebook level 2. At codebook level 2, we try to find the most similar codebook token embedding, the most similar vector. We try to find the most similar vector, we map it to it, and over here we map it to dimension this token 1, right? So now we take the previous residue, we subtract the new codebook level 2 vector, and now we get the remaining residue is at this level, the residue 2, right? And then we repeat this, right? We repeat this we keep repeating this until and along the way, we keep trying to minimize the residue. So essentially, based on this, we can now assign, given an embedding space, we can now assign it to integers or tokens, right? So now the semantic code for this is 714. So now if we take 7 plus 1 plus 4, the output of this will be the quantized representation. Essentially, what has come in, which is blue, we do this residual quantization. And when we take the respective tokens that are assigned to it, if we sum it all up, it should be the same as whatever has come in. And then based on this quantized representation with a decoder, we can get the original embedding. Any questions here? Did I lose everyone?
Where does, I mean, I read the paper too, and this part totally lost me. Where does that initial code book come from?
You initialize it randomly.
Okay. And so you start with,
or there are smarter ways to do this, which I'll talk about.
so you've got the random initialization, and then in this process where you're learning the representation, are you like iteratively updating the code book and updating
Yes.
the representation? Okay, that makes a lot more sense.
Yes. So this RQ-VAE needs to be learned. And when you learn this RQ-VAE, there are a lot of metrics to look at, which we'll see. And it's really hard to understand which metrics indicate a good RQ-VAE. Okay, so that's the semantic ID generation.
Quick question. Finally, when we try to calculate the loss of the quantized version and original version, at 714, do we actually do addition or there's some other operation actually? When I imagine that after training the code book, it will be deviate from the original initialization, so it won't be in the same scale, right? Addition may not make sense.
I actually do addition.
So just addition? Okay.
Yeah, I just do addition.
Okay.
And I think the image suggests addition as well.
I think
thanks.
they mentioned in the paper that they do 3 different code books for that reason, so that each code book has sort of like a different scale, so that you can they are additive.
Exactly. Because the residuals decreases with increasing levels, right? So that was what I explained via the image. I'm going to try to explain it again via the text in the paper, because I think this is really important. So whatever comes in is the latent representation, right? And we consider this the initial residue, which is R0. Now this R0 is quantized, essentially converted to an integer by mapping into the nearest embedding from that level's codebook, so R0. So now to get the next residual, right, we just take R0 minus the codebook embedding, right, over here. To get the next residual, we just take, okay? Then similarly, we recursively repeat this to find the M code words that represent the semantic ID. So this is done from cause to find. Now, there's this section over here, which I think is also quite important, that I really want to try to help us all understand. Essentially, now we know how we get the quantization, the input and output, everything. Now, this Z, you can see over here, which is really just a summation, of all the codebook vectors. This is now passed into the decoder, right, which tries to recreate the input embedding. So now imagine your codebook could be like 32 dimensions, and your input could be like 1,124 dimensions. This decoder now needs to map it from the input, the codebook representation, to the original input, and has to try to learn that.
Here we go.
Okay. So then the next thing is, what is the loss for this? So this is quite interesting to me. This is one of the first few times I've actually trained a RQ-VAE, and I spent quite a bit of time trying to understand this. I'll briefly talk through it very quickly, and then we'll go into the notes to try to see how to understand this. So the loss function is the reconstruction loss plus the RQ-VAE loss, right? And the reconstruction loss, this is straightforward, but the RQ-VAE loss takes a bit of time to understand. So now let's go into this. So the RQ-VAE loss, right, is the reconstruction loss, which is how well we can reconstruct the original output. This is quite straightforward. The original input is X over here. The reconstructed output is X hat over here. And this is really squared loss error. So how can we reconstruct it? Now that's quite straightforward. But the quantization loss, this one is a little bit more complex. You can see that there are 2 terms here, which is really SG. SG means stop gradient on residual minus the codebook and embedding. And then there's a beta term, which is how you want to balance it. And then the residual minus the stop gradient on the embedding. So you can see the left and the right is essentially the same, except the stop gradient is on different terms. So the first term this updates the codebook vectors, which is this which is this embedding here, to be closer to the residual, right? We stop the gradient so that we treat the residual as the fixed target. And now what this does is it pulls the embedding closer to the target. Okay? And then, so what this does is updates the codebook vectors to represent better residuals. Now, the second one is that it updates the encoder to return residuals closer to the codebook embedding. So you can see over we stop the gradient on the codebook embedding and we treat the embedding as fixed. So now the embedding is fixed. So now your encoder has to try to do the encoding so that it maps better to the codebook embedding. So essentially the first term teaches the codebook. The second term teaches the encoder. I think it's something like GANs. I'm not very familiar with GANs. But so yeah, I'm not sure if I can comment on that. Ted, I think vector quantization is a multi rounding up. Yes, I think the intuition is right. This is very similar. And then there's a beta, which is a weighting factor, right? So you can see in the paper, they use a weighting factor of 0.25. Essentially, what this means is that we want to train the encoder less than we want to train the codebook. And again, how do you choose this beta? It's really hard. I don't know. In this case, I think having high fidelity of the codebook is important because that's what we will use to train our downstream model. We're not training RQ-VAE for the sake of training an RQ-VAE. We're training over here, we're training RQ-VAE for the sake of having good semantic IDs that we can use in a downstream use case. Any questions here? Did I lose everyone?
I was like, I've just been building a variational autoencoder, so I'm a little curious. Like when in all my reading, there's always like a elbow or elbow-like loss. I don't see one there. Did you understand why they didn't use that, or is it just not mentioned? Or
they didn't use that. It's just not mentioned. I guess it's because when you look at RQ, and the RQ-VAEs didn't really come from this. It came from representing audio and also images. They cited these two papers, right? Residual vector quantizer. So Ted has a hand raised.
Yeah, so I don't deeply understand it, but I think I can answer RJ's question at a superficial level, which is that the elbow is used to approximate when you are training your regular continuous VAE, okay? And so you have some assumptions around like whatever normal distribution and things like that, that what you're trying to do is you're trying to do maximum likelihood, but you can't do it directly. So you use this elbow as a proxy in order to try to get to the maximum likelihood, okay? What the VQ-VAE paper says is that we're using a whatever multinomial distribution instead of this continuous distribution, and that's the reason why, because of that distribution assumption, we no longer have this elbow thing. I've never fully wrapped my head around it, but it's fundamentally because this discrete distribution is very different from the continuous distribution that we use with elbow. So somebody can go deeper than that. Yeah, that's as much as I got.
Okay, no, that's actually super helpful, and thank you for the. I'm gonna have to read those two citations as well. Thanks a lot, guys. That's helpful. Thank you.
Welcome. Am I going too fast right now, or is it fine? A bit too fast.
Maybe a high-level overview again for those that aren't following the technical deep dive. What is RQ-VAE, just in like one line?
The high-level overview is given some embedding of our item, we want to summarize that embedding. The embedding could be 100 and 1,000 dimensions. We want to summarize it into tokens, which is integers. And that's what an RQ-VAE does. So again, I think in this paper, the RQ-VAE is quite essential. I think the rest of it, this was the one that I had the hardest, the largest challenge to try to implement. The rest are quite straightforward. So I want to spend a bit more time here.
Can I ask a question?
Go ahead. Yeah.
That sum, it's the vector sum. You're summing the embeddings.
Yeah.
Okay.
Yeah, you just sum it up and you get the output. Is it fair to say the novel contribution here is intermediate token summarization versus textual? Yeah, it could be. Essentially, it's a way to convert embeddings to tokens, right? Firstly, you quantize the embeddings and you think about it, it's really tokens. What's a good choice for the number of levels? It's hard. I don't have the answer to that. But in the paper, they use 3 levels and each level has 256 code words. So that essentially can represent 16 million unique combinations, essentially 16 million unique combinations. So now let's go into the code. Of course, I won't be going to all the code. I just want to go through the part to help folks understand a bit more. I have this. Oh, see this. Okay, perfect. So you can see over here, the codebook loss, essentially that's how we represent the losses, right? The codebook loss is just the input, we detach it, the stop gradient, and the quantize, which is just the combined embeddings, right? The combined codebook embeddings. This is the codebook loss. The commitment loss. Go ahead. And the commitment loss is really we just take the quantization and we detach it, and we do mean square error on the input, right? That's essentially all there is to this loss, right? So that's how we implement it. Quite straightforward. Then, this is how we do the quantization. So you can see we firstly initialize some array to just collect all of these. For every vector quantization level, we take the residual, and the residual is really the first time at the very first input, the residual is just the input embedding, right? We take the residual, we pass it through the vector quantization layer, and we get the output. Then we get the residual for the next level by just taking the residual and we subtract the embeddings, right? That's the residual. Now our new output is we just keep summing up all of this. So our quantized output is just we just keep summing up. So if essentially at the end we can represent this initial residual by the sum of the vector quantization layers, and that's that recursive thing. That's all there is to it. Okay, maybe I'm oversimplifying it, but yeah. Then when we encode it to semantic IDs, essentially this acts as the embedding, right? We convert this embedding. So for every vector.
Hello.
Oh, yes, go for it. Is someone unmuted? When it should
Sorry,
be
Khaled is unmuted.
From
okay, maybe thank you for muting them. So the input is really the embedding, right? So for every vector quantization layer, and the embedding is the initial residual, again, we just pass it in, we get the output, and this output, we essentially what we want is the index. So the index, and then we get the residual. So we get the residual minus the codebook embedding, and then we just go through it again. So at the end of this, we get all the indexes for the semantic ID. And now that is those are, you consider them as our tokens, right? The SID tokens that we essentially saw here, right? This over here, this maps to the first index, 201, the second index, third index, fourth index. So essentially my RQ-VAE has 3 levels, and the 4th level is just for preventing collisions. I guess the last thing, initialize. Okay, the last thing the question that folks had, and this is what the paper does as well, which is how do you first initialize these codebooks? There's a very interesting idea, which is that we just take the first batch, and for each level, we perform k-means. And we try to fit it, right? And then after that, we just return the clusters. We do k-means with the means in terms of your KV size. So not KV size, in terms of your codebook size. So my codebook size is 256. So I want k-means with 256 means. So now I have all these 256 means. I just initialize it with these 256 means. And that's how I do a smart initialization. What does the fourth level in the RQ-VAE? My RQ-VAE only has 3 levels. The fourth level is something I artificially add when there is a collision in RQ-VAE. How to determine a codebook size? Again, that's a great question. I actually don't know how to determine a codebook size. It's really hard because we're not training the RQ-VAE just for the sake of training the RQ-VAE. We're training the RQ-VAE for the downstream usage. Ooh. Yes, I think that's a great example that of the VBOO of the image that VBOO shared. So now let's look at some trained RQ-VAEs to try to understand how this works. So I've trained a couple of RQ-VAEs. Not all of them work very well, but I want to talk you through this. So essentially, if you recall, their commitment weight, their beta was 0.25, right? So all of these, the beta is 0.25 unless I say otherwise. So let's first understand what the impact on learning rate is. Initially, I have 2 learning rates. The green learning rate is lower than the brown learning rate. So you can see, of course, the brown one with a higher learning rate, we get. Oh, first let me take some time to explain what the different losses means. Okay, so this is the validation loss. Essentially, the loss on the validation set. This loss total is really just the training loss. Now, if you recall, the loss of the RQ-VAE has 2 things in it. There's the codebook loss, and then there's the commitment loss. So now this is the reconstruction loss. You can think of it as if you try to reconstruct the embedding, how well does it do? Now this is the vector quantization loss. I didn't actually calculate the. I think this is. I can't remember. This is the. I think this is the codebook loss, right? And the reconstruction loss is the commitment loss, which is the reconstructed output loss. Okay, so you can see, and this is the residual norm, which is how much residue is there left at the end of all my codebook levels. Ideally, this demonstrates if you have very low residual norm, it means that your codebooks are explaining away most of the input residue. So a lower one is better. So of course, all the losses, the lower is better. Residual norm, the lower is better. Now this is a different metric. This is the unique IDs proportion. So at some period, I give a big batch of data, maybe 16K or 32K, give a big batch of data. I put it through semantic IDs, the quantization, and I calculate the number of unique IDs. So you can see that as we train, the number of unique IDs gets less and less. Essentially, the model is better at reconstructing the output, but it uses fewer and fewer unique IDs. So what is a good model? I think what is a good model is quite hard to try to understand. But here's what one person responded. And the response kind of makes sense. So that's what I've been working on. So look at validation reconstruction loss. Again, how well is your RQ-VAE good at reconstructing the input? The quantization error, again, this is your codebook error. And codebook usage. I think of this as unique IDs as well as codebook usage. We also see some graphs of codebook usage. Okay, so now you can see that with a higher learning with a higher learning rate, which is this one, this learning rate is higher than the green, we have lower losses overall. But our codebook usage is also lower. So I think that's one thing to note. Again, I don't know which of these are better. Is it lower loss better or codebook usage better? In the end, I just took a step and just picked something. Now over here, this are, I think maybe this is just easier to compare. These are the various weights, right? If you remember, this is the commitment weight. This is a commitment weight of 0.5, and this is a commitment weight of 1. Essentially, the commitment weight is how much weightage you want to have on your codebook, right? On your commitment loss, on the validation, on the reconstruction error. So you can, and this is commitment weight of 0.25, which is the default. So you can see with a higher commitment weight, our reconstruction error is actually very similar, right? But when we push the commitment weight up to 1.0, you can see something really off goes here. Our loss is a lot, just acts very funkily. You can see our loss is just very high, but the unique IDs is also higher, which is actually better, and the residual norm is lower, which is a good thing. That means we explain most of the variance. So in terms of how to figure out how to pick a good commitment weight, I think it's very tricky. I haven't figured it out. Essentially here, when I double the commitment weight, I have lower validation loss, and my ID proportion is similar, but my residual norm is higher. But in the end, I just stick to the default, which is 0.25. And over here, this is another run I did where I cleaned the data. Essentially, I excluded the product data, and all of this is like open source Amazon reviews data. I clean the data, exclude those that are unusually short, remove HTML tags, and you can see by cleaning the data, you can get a much lower validation loss, much lower reconstruction loss. Residual norm is similar, but your unique ID proportion is a lot higher. Does that make sense? Am I going? Yes, the reduced number of unique IDs. Am I just going too deep into this? But I also do want to share a lot. Okay, we just take. Okay, maybe I'm going too deep into this, but I'll just take one last thing to show you how a good codebook looks like. So this is the codebooks. So these are the codebooks, right? And this is the distribution of codebook usage. This is a not a very good distribution of codebook usage. You can see all the codebook usage is in token number 1, right? And you can see there's very large spikes. So this is when your RQ-VAE is not trained well. You don't have a very good distribution. And then you can see over here, where's my numbers for? You can see over here, the proportion of unique IDs is only 26%. That means all your data, you've only collapsed it to a quarter of it. Essentially, you've thrown away 3/4 of your data. But what happens when you have a good RQ-VAE? Here's how it looks like. The proportion of unique IDs is 89%. But this is the codebook usage. You can see the codebook usage is very well, somewhat well distributed, and all the codes are well learned, and all the codes are fairly well utilized. So this is what it means by having a good codebook usage. Any questions here on RQ-VAEs? Did I lose anyone? Everyone? Is this code available anywhere? Yes, soon when I clean it up, maybe over the Labor Day long weekend. But it may take a lot more time. The code is very messy.
So what have you done so that you can have a good code distribution codebook?
The main thing that I have done is, so a few things. They use k-means clustering initialization. So I do that, k-means clustering initialization. The other thing I do is codebook reset. So essentially, any time, at every epoch, if there are any codes that are unused, I reset it. So essentially, I'm just forcing, I reset unused codes for each RQ-VAE layer. So I'm forcing the model to keep learning on those unused codes. Seems to work decently. Yeah. So the next thing, now we will very quickly go through the recommendations part of it because I think it's fairly straightforward. So, oh, Michael has a hand raised.
Hello.
Yes.
Hi, Eugene.
Yes.
Yeah, I'm a South Indian, and I am right now entering into this AI field. So right now, what do you suggest and how to enter into this field as per the new concepts that are right now in your point of view?
Yeah, I think a great way to learn this is I'm gonna share an invite link. A great way to learn this is really just to hang out in the Discord channel. So I'm gonna copy the link. I'm gonna paste it in the chat. I think the really just is just learning via osmosis, right?
Yeah,
What are the folks? Yeah.
Yeah, due to this AI boom, I have learned the no-code development, N8N, and all these things for almost 4 months. But right after, I have sort of issue I found out, right, because the coding. So I have
Yeah, thank you,
found due
Michael.
to
What I would do
this.
is to really just ask on the Discord channel. And the thing
Okay.
is, the reason why I'm saying this is there's only 15 minutes left and I still have quite a bit I want to share and go through, share with
Yeah,
you.
I
Anyone
respect
has
your
any
time and
questions
same with
related to
you.
the paper? Frankie?
Question.
Okay.
Can you hear
go
me?
ahead.
Yes.
Yeah, a quick question. Maybe it's not relevant, but I noticed that you did some stop gradient. So you're stopping backpropagation. Is that because you're trying to freeze something when you're doing training? I don't quite understand.
It's just firstly, it's part of the RQ-VAE formulation where they do stop gradient, right? And so I'm just following it. And the reason is if you don't do stop gradient, if you don't do stop gradient, this is the loss function, right? It just simplifies to this, right? Which is residual minus codebook embedding. So now this leads to a degenerate solution, right? You can imagine that your encoder will just encode everything to 0, 0, 0, 0. And your codebook will just encode everything to 0, 0, 0, 0. And essentially you just use one single thing where they both cheat.
Okay, but then you have to allow training at some point, right? Because you're training the code book. So how does that codebook get modulated then if you do stop gradient?
So we do stop gradient on the residual for the first half of the RQ-VAE loss equation. And then we do stop gradient on the codebook for the second half of the, and then it's a
Thank you.
weightage. We weight it
Got you.
by.
Yep, I see it. Thank you so much. Yep.
Okay, so I know we have some questions left, but I'm gonna take 5 to 10 minutes to try to go through the recommendations part of it, which is really where it all comes together. And we also have results for that. So I'm gonna ignore the questions for a while. So now generative recommendations, right? What do is we essentially construct item sequences for every user. We sort them in terms of all the items they've interacted with. Then given a sequence of items, the recommender's task is to predict the next item. Very much the same as language modeling. Given a sentence, predict the next word in the sentence, right? Essentially, that's what SASRec is, what a lot of our recommendation model is right now. So, so for a regular recommendation, given a sequence of items, you just predict the next item. For a semantic ID-based recommendation, given a sequence of semantic ID, you predict the next semantic ID, which is now not a single item, but a sequence of 4 semantic IDs. So now the task is more challenging. You have to try to predict the 4 semantic IDs. All right. So you can see that they use some data sets here, and they have the RQ-VAE, which we spoke about. There's an encoder, a residual quantizer, and a decoder. I think the encoder and decoder is essentially the same thing. I mean, not the same thing. It's just mirror image of each other, different weights, of course, as well, and residual quantizer. So you can see they have a sequence-to-sequence model implementation. And this is their codebook, right? 1024 tokens. It's only 3 levels, and the 4th level is for breaking hashes. They include user-specific tokens for personalization. In my implementation, I didn't do that. Now let's look at some SASRec code. for the recommendations, and we'll see how similar it is to language modeling. So over here, this is the SASRec code. And if you see, it's actually very similar, right? You see modules like causal self-attention, which is predicting the next token. You can see the familiar things, attention, number of heads, etc. And then, QKV. And then you have your MLP, which is really just ReLUs. And then the transformer block, this is a pre-layer norm, self-attention, layer norm, and MLP. That's it. That is our recommendation system model. So now the SASRec is item embedding. For every single item, we need to have a single item embedding, position embedding, and dropout. And then the blocks are really just the number of hidden units you want and just transformer blocks. And of course, a final layer norm. For the forward pass, what we do is we get all the item embeddings, we get all the positions, and we combine it. So now we have the hidden states, right? Essentially, what has happened in the past. This is what has happened in the past. Now for the prediction, we take the hidden states, which is the past 5, 6. Now imagine this is language modeling. We take the past 5 to 6 tokens, we forward it, we get the next language token, candidate embeddings. You can see now we get the candidate embeddings. And what we do in recommendations, what we do in recommendations is we score them, and the score is really just dot product. Essentially, given what has happened in the past, we encode it, we get a final hidden layer. Given all the candidate embeddings, we do a dot product, and that's the score. So essentially, given all the sentences, given all the potential next tokens, get the dot product to get the next best token. And that's the same for recommendations over here. And the training step, I don't think I'll go through this. I won't go through this. Now for SASRec semantic ID, it's the same, right? Now this is the forward pass. No, this is not the forward pass. For a SASRec semantic ID, this is the same. Predict next item. So now you saw that previously we were just predicting only one single next item. Now in this case, we have to predict 4 tokens to represent the next item. So when we do training, we apply teacher forcing, whereby first we try to predict the first token. If that is correct, that's fantastic. We use that first token to predict the next token. But if it's wrong, we replace it with the actual correct token. So that's what we do when we do training. But when we do evaluation, we don't do this. When we do evaluation, you can see, okay, I'm definitely losing people here. So I won't go too deep into this, but when we do evaluation, we actually don't try to correct the evaluation. So now let's look at some results of how this runs. Essentially, when I was doing this, all that I really cared about was, do my semantic IDs make sense? So let's first look at this. This is a SASRec model. You can see the NDCG is unusually high, right? So firstly, the purple line is the raw SASRec that just predicts item IDs. Given the past item IDs, predicts the next item ID. Let's just look at hit rate. Right, you can see the hit rate is 99%. I made it artificially easy because I just wanted to get a sense of whether there was any signal or not. You can see hit rate is 99%. We exclude the most infrequent items. There's no cold start problem over here. And the false negatives the false positives are very easy to get. So you can see this is how the regular SASRec does with NDCG of 0.76. Now let's look at our semantic IDs. Now, again, to be very clear, right? Semantic IDs, the combination of semantic IDs that are possible is 16.8 million. But in our data set, we only have 67,000 potential data points. So the fact that if from that 16.8 combinations is able to even predict correct data points, that's a huge thing. So over here, we can see that after we train it, the hit rate is 81%. That is huge. Essentially, it means that the model, this new recommendation model, instead of predicting the next item, it has to predict 4 next items, the 4 tokens that make up the next item. And only if that is an exact match, we consider it as a hit rate, right? Recall. And it's able to do that. And you can see that the NDCG is able to do that. On NDCG is also decent. So now it doesn't quite outperform the regular SASRec, because this is it would outperform it if we had cold start items or the very dirty items. I think it could beat or even match. But essentially this was all just a test to try to see if we can actually train such a model. Now that this test has passed, we know that our semantic IDs are actually working well. Now we can fine tune a language model, right? This is fine tuning a language model. You can see that this is the learning rate. So initially, this is my original data. You can see, maybe I'll just hide this first. This is training on my original data, and you can see my original data. This is the validation. My original data was very huge. There was a lot of data. Because I didn't really clean it, I just used everything. I was just not sure whether it could learn or not. And I found that it could learn. So let's look at an example over here. This. So you can see over here, this is the initial prompt, right? And it's able to say things like, let's look at test number 3. If product A has this ID, if product B has this ID, what can you tell me about their relationship? And all it sees is IDs, but it's able to say that they're related through puzzles. And then list 3 products similar to this product, right? I don't know what this product is, but I do know that when I look at it in the title form, this is what I expected. It was able to respond in valid semantic IDs. So what this means is that, hey, this thing can learn on my original data. So then after I clean up my original data, so now this is my new data set. You can see the new data set is half the size of the original data. When you can see, when we have this sharp drop during training loss, essentially that means it's the end of an epoch. It's a new epoch. But evaluation loss just keeps going down as well. And the final outcome we have is a model like this. This is a checkpoint from the first epoch, whereby it's able to speak in both English and semantic IDs. Okay, that was all I had. Any questions? Sorry, I took so long. Kishore, you have a question?
Hi, Eugene. So you said that when you notice some code points are being unused, you reset them. After you reset, did you notice them getting used? Do you have some metric to track the reset one actually was if the resetting was actually helpful in that case?
Yes, I was able to track that. Sorry, I'm just responding to Harris. Yes, I do have that. In my let's look at this. When I was training the RQ-VAE, I had a lot of metrics. I only went through just a few of them. But this is it. This is the metric that is important.
Sorry, you're
so
sharing
first,
something?
Oh wait, are you? Oh wait, I'm stopping.
You stop
sharing. Sorry. Okay, here we go. First, let me reset the axis. Okay, so the metric that is important is this codebook usage. So I do log codebook usage at every epoch. So you can see at step 100 or at epoch 100, codebook usage was only 24%, 20 to 24%. But as you keep training it, codebook usage essentially goes up to 100. So that's the metric I logged.
Nice. Thanks.
You're welcome. Frankie.
Yeah. Can you go over like again for the semantic ID part? What is the training data? Because I'm having a hard time understanding like what do you actually what is the LLM learning? So can you explain that again?
For training the RQ-VAE?
No. For the semantic ID part, the last example, because you're basically inputting, say, a semantic ID and say, how are these two things related to each other? And I'm having a hard time figuring out like what is it actually learning? Yeah.
So this is the training data. So essentially, the training data is a sequence of items. So you can see this is the raw item, right? And for each item, we map it to this sequence of semantic IDs. So now we're trying. trying to pick.
Does the order in this list matter or not?
Yes, the order matters. It's essentially the sequence of what people transact.
Okay.
And
then,
if the order in the semantic ID matters as well. For example, if we were to swap the positions of SID 105 and SID 341, it wouldn't make sense. That would be an invalid semantic ID. And the reason is because the first codebook vocab, the first number should be between 0 to 255. The second number should be between 256 to 511, and so on and so forth.
yeah, so that makes sense. I mean, but I'm talking about like in the group of 4. So if you permute those, does that matter? So
It does matter.
Does matter as well.
Yeah, it must be in this order. If not, it would be an invalid semantic ID.
I understand, because you have to go with your levels, right, of your coding, right? So you have 4
Correct, correct.
tokens. So that I understand. But I'm saying that you have multiple items here, right?
Yes.
So if you permute those, does it matter?
I don't know. I think it depends. It may or may not. So essentially, if I were to buy a phone and then you recommend me a phone case and then pair of headphones and a screen protector, that makes a lot of sense. But if I were to buy a screen protector and you recommend me a phone, that doesn't make sense. Right? In terms of recommendations and user behavior.
Okay, so that's encoding. That's the sequence encodes that behavior. That's what you're saying.
Yes,
okay.
that's correct.
Okay.
Any other questions?
Yeah, Eugene, I had done a lot of work on vector quantization, and there are some other techniques to handle like underutilization, like splitting. And one important question is the distance metric. Like I noticed that you're using Euclidean distance to measure the difference between the embeddings and the code words. But Euclidean distance is not good when there is a difference in value or weight for the features. So have you tried different?
Oh, I'm sorry, I'm in a noisy environment. Please go ahead.
Okay, so have you tried different metrics like Mahalanobis distance or something else?
I have not. Essentially, my implementation reflects what was written in the paper. So, and I'm not sure if I'm really using Euclidean distance. I can't remember where is it. Yeah, but it's worth a try. But I just used the implementation written in the paper and it works.
It's in the main equation where you have the subgradient, because that sign is the Euclidean distance, and it is by default what K-means algorithm uses, but you can change that.
So then that's what I'm using. Yeah. So I just replicated that. Any other question? Oh, Pastor, you have a question?
Yeah, so I have a question related to that. So in the paper says that you use k-means to initialize the codebook, and then you use it for the first training batch, and then you use the centroids as initialization. Is that what you use? And follow of that, it also says that there is an option to use k-means clustering hierarchically, but it lost semantic meaning. So I didn't really understand that part. If you can briefly explain, and if you use the centroids as initialization. Thanks.
So yes, that's what I used. I'm sorry, what was your second question?
Yeah, so also the paper said that the other option is use k-means hierarchically, but it lost semantic meaning between the clusters.
Yes.
So yeah, do you know why or how that plays, or what's the difference between using the what is suggested in the paper?
That's a great question, right? So are you referring to this? They use k-means clustering hierarchically. Essentially, these are different alternatives of quantization, right? Over here, we quantize using an RQ-VAE. They also talk about locality sensitive hashing. Then the other one is they use k-means clustering. First k-means, then second level k-means, and third k-means. I don't know why it loses semantic meaning. Honestly, so
Okay.
I won't be able to address that. I haven't actually tried this. Yeah, and I don't have a strong intuition on why it loses semantic meaning.
Okay, cool. Thanks.
Yeah.
I can try to answer that. Like when you're having the same ID and you're using the proper k-mean clustering, the entities are unique and they represent something. But if you try to split them into different levels, like the first order, and you group them, and then you do grouping of the second layer, as if like you're trying to cluster numbers. If you keep a 3-digit number, 973, and cluster it with 821, then they are close together. But if you cluster on the 100 digits first, then the tens, and then the ones, you lose the meaning, and these numbers do not become close to each other.
Awesome. Makes sense. Thank you.
Okay, well, very much over time. Thank you, Vibhu, for kindly hosting us for so long. I can stay for any other questions.
Feel free to take Eugene's time as he has questions. For next week, we have a volunteer for a paper. I'll post it in the chat right now. But yeah, thank you, Eugene, for presenting. And same thing, if anyone wants to volunteer a paper to present the following week, now is your shot. You'll definitely learn a lot going through the paper, being ready to teach it to someone. Otherwise, the paper is how do language models memorize?
And also to be clear, I want to make it very clear, right, that I did not prepare for this over the course of a week. So if you're preparing for a talk like this, I've been working on this for several weeks, ever since like 4th of July holiday, right? And essentially this is just, I've been working on it, I'm excited to share about it with people, and that's why I'm sharing. Most of the time we usually just go through a paper. So if you want to volunteer, it's okay to just have the paper, that's it.
If you want to see the other side of, the other extreme, unlike Eugene, who prepares for months, I read the paper the day before.
The day, or the morning of.
Hey, don't call me out. Yes,
But Vibhu has slides. That's the thing. I will never have slides.
No. I used to do slides. I actually think it's slightly detrimental. I don't think it's as beneficial to make slides out of papers anymore. Papers are good ways to read, to understand information. So now it's just walk through a highlighted paper, just read it, understand it, and yeah. Well, okay, take Eugene's time asking him about semantic IDs.
Yeah, and we can also go through more of the paper if you want. I know I haven't gone through as much of it as I should, but essentially the answer is there, and the results replication is very similar. Kishore, you have a hand raised.
Hey Eugene, so while you're implementing this, right, was there anything from the paper that you could not replicate, which you had tried?
I think it took me a lot of time to try to train a good RQ-VAE. And that's why I spent so much time on it. So essentially, to train an RQ-VAE, you see that I had so many experiments, right? Gradient, I did crazy things, stop gradient to decoder, gradient clipping, and a lot of it failed. I even tried, like there was this thing called exponential moving average to learn the RQ-VAE codebooks. Like it has great unique IDs, right? But it's just not able to learn. You can see that the loss is very bad. And that was because I was new to this. So you can see that the loss, actually, if we zoom in on only those after 2000, you can see the loss of this.
Zotero.
Oh, shoot, you only see Zotero.
Uh-huh.
Thank you. I shared my desktop. Thank you for So you can see I tried some crazy things like this exponential moving average approach to update my codebooks. So you can see the purple line is the exponential moving average. You can see the loss is very high, and it just doesn't work as well. Like gradient clipping, the rotation trick, figure out what the right batch size is, what the right weight is, what the clean data is. So this took me several experiments, and that was after even deleting the experiments that just don't make sense to save. Whereas the recommendation part, I just needed 2 experiments. And you can see, yes, even though that the recommendation loss is the hit rate and NDCG is not close to the SASRec one, the intent was never to do that. The intent was can a SASRec actually learn on this sequence of 4 tokens? And very quickly you find that yes, it can learn. And then that's when okay, now let's not train a SASRec from scratch. Let's train let's fine tune a Quen model from scratch. And this was not part of the paper. This was just for my own learning. You can see the paper uses all these recommendation models. But yeah, that's it.
And because I'm also planning to train an RQ-VAE, is there some good places I can start with? I remember there should be some official repo for that on GitHub if I'm not wrong. I remember seeing that a while back.
Well, I wish there was, but I definitely didn't come across that. But what I would recommend is essentially this is my recommendation. It's very great for learning, especially now with things like Cloud Code, to try to code this up from scratch. You really learn the nitty-gritty things, right? About how that code is actually represented. And yeah, I think Khaled was right. I was using Euclidean distance. And this is the distance I was computing. So, but yeah, I don't know, maybe there's a better distance. I certainly haven't gone as far down the road. I just took the default implementation and just followed it.
Makes sense. Thanks for answering the questions, Eugene.
You're welcome.
Eugene, quick question on your highlighting. What does red and green mean?
So over here, so green means good, right? Like these are the benefits. Training allows knowledge sharing, atomic item IDs, and then red is the downsides, right? Essentially, when we're considering a new technique, what are the downsides? So with the regular SASRec, if I had to train a regular SASRec and I had 1 billion products, my embedding table would be 1 billion products. But if I had 256 with the power of, with just a 4-level codebook, 256 with 4 levels, I can represent 4 billion products. And that's just 1024 embeddings, right? So instead of 1 billion embeddings, 1 billion level embedding table, I just need 1,000 level embedding table. And that saves you a lot of compute.
I see. Thank you.
You're welcome. Kishore has a hand raised. I assume Kishore has asked his question. Frankie, you have a hand raised.
Yeah, so I think it's similar to what you just spoke about. I had a question about if you do the 2-tower one, you have 2 encoders and they're trying to like create this embedding that approximates whatever query and item. So it creates an embedding. And so I think you tried to explain a little bit just now, but I tried to understand why is that embedding worse than this one that's creating by, whatever your quantization steps, right?
The embedding is not worse. I think the embedding is probably just as good or even better.
Okay.
But there will be a lot of those embeddings. So imagine if we had 1 billion products, we will need 1 billion embeddings, 1 for each product, right? But with semantic IDs, if I have a 4-level codebook, because each codebook can represent 256, and assume each codebook can represent 256. Can you see my raycast?
Yes.
So imagine each codebook can represent 256, right? And then the combination, all the permutations of this codebook is actually 4 billion. Now I don't need 1 billion products. I just need 256 times 4. I don't need 1 billion embeddings. I just need 256 times 4 embeddings.
So in some sense, I kind of think of it as a better encoding of what it is, right? So you're saying that I can more economically compress that
More economically compressed. Yeah, I think economically compressed is the right term. So, And the reason is because, at least in my, so in the paper, they showed that using their generative retrieval, they were able to achieve better results. That's not something that I was able to replicate. And also it's because their data sets are actually kind of small. Their data sets are actually very small. Right, you can see that their data sets is like very few items. I deliberately chose a data set that was much bigger, and maybe with a bigger data set, again, I don't know how this would scale with a much bigger data set. My data set is at least 4x bigger than their largest data set. And I actually want to scale this to million level data sets, right? So that's one thing I haven't been able to replicate. But again, you can see here that it's not stupid. This idea is the model, even a regular SASRec, is able to learn on the sequence of token IDs. Yeah. Any other questions?
Hello, Eugene. Sorry, the hand raising function seems like very me. I just asked directly.
Okay.
So I'm curious that for the SASRec models and the Quay model that you fine-tuned, have you compared the performance of those in terms of next Semantic ID recommendation?
So obviously the SASRec model is way better. The Quen model is not as good. But the purpose of the Quen model is not to be better than the SASRec model. Right. The purpose of the Quen model is to train to have this new capability whereby users can shape their recommendations. Essentially, you can imagine this like chat, right? Hey, it's the convergence of chat. It's the convergence of recommendation systems, search, and chat. That is the intent.
In the sense that it's have more general interface than the SASRec that mostly like a recommended semantic ID in this case. If you will build a chat model, then this Quen model could be helpful.
Yeah.
Yeah.
So Flo has a great question. What is this model param size? So let's look at it. Do I have logs? Please tell me I have logs. Yes, I do have logs. Fantastic.
Eugene, you're not sharing your screen again.
Yeah, I'm showing my screen now. Okay, so you can see this is the regular SASRec model. You can see we have these users, and this is the total parameter size. It's only a 1 million parameter model, right? And then when we train it on, and then for the larger SASRec model, which is the one with the tokens, oh, it's a 7 million parameter model. Yeah. So yeah, whereas Quen is like 8B. So yeah, it's a lot smaller. But for recommendation systems models where you're just predicting a next best token, you don't need something so big. There's no benefit from additional depth in your transformer model. Okay, I guess the questions are drying up. Okay. So that's it then. Thank you for staying.
Excuse me, Eugene.
Hey, Khaled.
Yes. So the semantic ID, is it only 4 levels, 4 digits?
In my use case, I only use 4 digits. But you can imagine this to be you can make it 8 levels. At every codebook level, you can have more codebooks, more code words. In my case, every codebook level is only 256. So you can have it as wide and as deep as you want to.
Okay.
And again, how to decide that is very, very difficult. Because if you know of a way, please share with me. I don't know of a way that I can assess if my SASRec is good or not. No, I don't know of a way where I can assess if my model is good or not. My RQ-VAE, the value of my model is actually the value of what it does downstream. So that is tricky. So I have some RQ-VAE run analysis. So essentially with all the different ways, like what the different unique IDs are. So essentially, eventually what I did is I prioritized validation loss and the proportion of unique IDs. And also not too many tokens, because that makes real-time generation in the chat format. If you have like, if your semantic ID is like 32 tokens long, then in order to return a product, you need 32 tokens, which is not very efficient. So I just chose to have 4 tokens long.
Yeah,
Eugene, I think
there are
in
other ways, you know, to measure that. You mentioned 2 of them, but you can also look at the perplexity or codebook like token efficiency, and
What does that mean?
like how many tokens are needed to achieve good performance in your opinion?
But what is the measurement of good performance then?
Yes, there are some practical characteristics, like scalability. Can you add more data and you see it's able to handle that? And how, like inference latency, how long will it take to try, you know, to see what are the recommendations?
Yeah, inference latency, I think, is a function of the codebook depth, right? So with more codebooks, more code levels required, you need more tokens, which is inference latency.
Yeah.
Okay,
Yes,
sorry.
you're right.
Someone else
Go
had a
ahead,
question?
sorry. Yeah.
it was not a question. I remember seeing in a paper where they evaluated the code words which they learned. I think they did something like a visualization where they could get the taxonomy, and they showed that each taxonomy made sense, where each the code word and then below that all the subcode words were, I guess, something more like categories and subcategories. I don't know if it was the same paper we showed that. Maybe
It's
that
the
is
same paper. It's the same paper. Yeah, they talk about it. Whereby, yeah, it's over here. What this visualization shows is that our semantic IDs have meaning, right? So it tries to show that, okay, this is how is that, like, how do you interpret it, etc. But for me, I don't really need them to have meaning. It's okay to have a meaning that I don't understand, so long as it performs well on my downstream task of blending language and recommendations together. So you can see over here, this is like the Amazing Spider-Man, right? Mario-like products. I guess it equates it to Nintendo-like products. Donkey Kong, Zelda, Donkey Kong. Yeah, so I don't know, let me try a PlayStation product for Spider-Man. What comes out? Last of Us, PlayStation 3, Last of Us, Metal Gear Solid, PlayStation. So essentially, I think this is what is interesting to me.
Evaluating at that level will kind of act like a unit test for the RQ-VAE, right? Because evaluation at this level in the downstream, it could also be that maybe your recommendation model is bad, maybe, but the semantic ID is
Exactly.
right. No?
Exactly. Yeah. So, but the thing is, this visualization they had over here is very, very difficult to do. You have to look at it. You have to try to find the metadata to map to it, and then try to look at it, right? But it's very challenging. Like, how do you measure what is a good distribution? I guess you can measure KL divergence, or you can measure, you have good measures of distribution, but it's really challenging.
Do you think we could initialize the code word so some categories you have internally for your own products and use that maybe?
I don't know. I think, honestly, I don't know. I think it might be hard. Yeah. Vibhu, you have a question?
I'm curious, in your model, if you tried, instead of passing in semantic IDs and like natural language query, if you pass in just a natural language question, does it predict your semantic IDs properly? So like if you know you have a query for Zelda, if you just ask it like, what is a game with a princess and a guy Link and this and that, can you get it to start outputting semantic IDs, right? As opposed like, and let's say like you really prompt it, right? Like normally you would expect the LLM, it's still based on LLM backbone, it would predict
it would just use normal text, right? Like it would say the word The Legend of Zelda. But if if you few shot prompt it and you tell like you must answer with a semantic ID. So like right now
So you can
it's
see,
using.
I just finished The Amazing Spider-Man, recommended our product. That's wow, this is insane to me. It's like this is really, I don't know where the limits of this. I think it's not very smart. So clearly, let's just say firstly, it's not very smart. The recommendations are not very good. But the fact that you can do this and it can return you semantic IDs that are in your catalog. My God.
I mean, I
I'm
think
just
there's also there's the other side of just naive overfitting, right?
wow.
If I do
Oh
none
yeah,
of
of
this
course.
training, if I just have like regular SFT and start adding tokens, the model
Yes.
will use them, right? The value is
Exactly,
in
exactly.
proper embedding, understanding
What
of
is a
what
new
these
game?
tokens mean.
Mass Effect. I don't know. Okay, I mean that shows how old I am. I just finished
Elden Ring,
Elden Ring. Okay.
Wukong.
I don't know. I know. I honestly don't. I honestly am not able to. So firstly, this is a gaming that I don't know if this is a good game, but at least it's like same level of maturity. It's not like a
I
Donkey
think
Kong.
the fun little evals you can do here to test if these are learned is like you have expectation correlation, right? So like if you finish a Souls game, will it recommend you the next one, right? Like before Elden Ring, or if you do like Civilization 4, will it recommend
Ooh,
Civilization 5, right?
I don't even know if
And
Civilization 4 is in the data set. Wow, I actually don't know. Sounds bad to me, but yeah.
but it's interesting nonetheless. And then I'm curious, like, can you just use it as a chat model? Like if you just say like, what's the weather in New York in July, does it output games? chat model.
Wow. So firstly, hallucination, but second, it maintains English language.
And thirdly, the pavement's melting.
Oh yeah, I don't know.
75
Exactly right.
Celsius, they're so cooked.
Okay, now here's a crazy test. I like sci-fi and action games. Ooh, I am not able to evaluate this. Because I don't know about this game, but fantasy and let's say cute. Sounds bad.
Ask it about like a niche game that not many people have played, and then we see if people have played the game.
Yeah. I don't know. I like Animal Crossing. Again, this data set is very old. So, but you can see it's like now you can talk to it and it can return you things that are in the catalog. So Ted, you have a hand raise.
I don't think this is important, but since you're just playing around, one of the things when I do these kinds of things is I like to take the recommendation and then just flip it to see whether it sends me back to the same, right? So sometimes you get like a pair that just go back and forth, or you get a ring. But if it doesn't, if it's just kind of doing a random walk, that's usually a bad sign. Does that make sense?
Yeah, it makes sense. Let's try this. Super Mario Bros. Recommend me another game. Okay, user has done Super Mario Bros. Let's do this. Ghost Squad. Ooh. Returns you exactly the same thing.
Ghost Squad isn't a tractor.
Yeah, it's like a black hole that.
I think
All right, but
it's
anyway,
time.
but you could try this
Ghost
with some
Squad to
things
Splinter Cell.
and just see if you know.
Oh. Is Ghost Squad
I
part
like
of Splinter
this.
Cell? Yeah, it could be. Very interesting. I actually have no idea how this model is learning.
I feel like it would be
Wow.
fun to do one of these and
More
interpret it
complexity.
with more like familiar categories and
So you can see Splinter
items,
Cell to
right?
Rainbow Six. Yeah, and then the next thing is clearly the obvious next thing to do here is Macintosh. Once you have a model that you have access to weights thing. But
All right, I'll create some binary probes for some linear probes for your model.
so I hope to release this soon, like at least the model weights. And then folks can play. It'll be dumb, but it's just a fun idea that I've been brewing for a while. Thank you, everyone. We're half an hour past our
This is
internet time.
very interesting, Eugene. As I said, if there is a chance that we can discuss, I have a lot of ideas for vector quantization and also
Thank you.
some measures of that.
Feel free to put it in the LLM paper club chat and just tag me, and then we can just chat there.
Okay.
Thank you, everyone.
Thank you.
This was
Thank
great.
you. Thank
Thanks,
you.
Eugene.
Stop the video. The recording. It should stop on its own, right?
It does. Yep.
Okay.
I'll stop.
Okay.
Take care.
Thank you.
See you guys next week.